We also want to talk about arrays and lists. Now, this is a really fun topic, especially when we get into C++ and we start getting into the object-oriented concept of things. We can then really fully understand together the difference between the classical array and the modern array list, or they used to be called like linked lists and that sort of thing, dynamic arrays.
So a variable is of a certain type, or a certain data type. So variable x can be a number, or variable x can be a letter, or variable x can be some word, or
Boolean?
some sentence, or some true or false value. So what type that is considered to be a data type. And in a classical array, you have a series or a set of a particular data type. So a set of integers, or a set of floating point numbers, or a set of characters, or an array of characters.
And one of the important things to understand about the classical array is that the size of the array is defined before. So you can't have, if you are reading in a file, you actually have to say, well, the maximum size of the file that I'm going to allow is this. Because that has to be predefined. You can't just have data coming in random succession, and if there's new data, just append to the bottom. That problem was fixed a little bit later on when we get into the more modern implementation of arrays, which is essentially a list of objects that can be the same or multiple types. They don't have to be the same type anymore. Yep. And there is no predefined length. As long as you have memory available in your computer, you can keep adding values. The second you run out of memory, your program will crash, but as long as there's free memory, you can keep appending values.
So these are also considered to be linked lists, array lists, dynamic arrays, those kind of things.
You'll hear it mentioned in those contexts. So what we want to do right now is kind of show you visually what an array looks like. Now, arrays can have multiple dimensions, which we'll get to in a second, but this is a basic example of an array. So we just have a list. Now, on the top bar, there's just numbers from 0 to 4. That's the index value.
Or the positional value.
So in arrays, in any language worth its salt, arrays will be indexed starting at 0 up into a value.
So in this example, the size of the array would be 5.
Right.
So 0, 1, 2, 3, and 4 is 5 elements contained in this array.
So when we store values in this array, they just append to these values. So if I say, array, I want index element or subscript 2, that's going to come back as value 3.
Right.
So
you can see this as a sideways file cabinet, where the top drawer is 0, the next drawer is 1, and so on. So when you open up drawer number 2, you look what's inside, and inside of it is value 3.
Exactly. Now, a list, a linked list, an array list, a dynamic array, they kind of work a little bit different.
Absolutely.
So if you kind of look at this grid, let's pretend like this is memory. And memory is addressed. So in our little example here, if you want to find what's in memory address 2, 3, you would go over 2 and down 3. So just to kind of get us all on the same page. Now, a dynamic array always starts off with a pointer, which we'll get to in a second. But in basic form, a pointer does nothing else but point to a memory space.
Right, a particular location in memory.
Right, so when we create this dynamic array, we have a starting point that stores the location of the first value. So when I create a value, here I have value number 1 in this example. Number 1, which is the value, is called a node. So the pointer points to a node, and every single node contains its own pointer. And the pointer that connects to a node points to the next element in the list.
Absolutely.
And there's also some more advanced lists that are bidirectional, where there's 2 pointers stored. It stores the next and the previous value. So here, I'm looking at 1, 4, which is value 1. The next value that we add is just thrown in memory space 2, 1. So my pointer points at 2, 1. Then my next memory value points here, and my next memory value points here. Finally, the end of my array ends here, and I have a little black circle here to indicate this is the end of the list. And we kind of alluded to this before, but arrays can have multiple dimensions. So Brian, explain, what is a multidimensional array?
We're looking at it from math. If you have familiar with math, multidimensional array in its most basic form can be seen as a Cartesian product or a multiplication table.
Yeah, there you go.
So if you remember, the array is a sequence of things. It's a series of things. If every element in that series was another array in itself, then you have a multidimensional array. So if you go to element number 3, just to find that it's a 5-element list, you have an array. Another form of multidimensional arrays, or a 2-dimensional array, would be a Excel spreadsheet.
That's a great example. But they also expand beyond 2 dimensions. 2 dimensions seem to be, in most practical applications that are application-oriented, not graphics-oriented, 2 dimensions are usually the most you'll see.
Right.
But, Brian, you're much better at kind of explaining this. There are also 3, 4, 5, 6, 7, 8, 9, 10, 11, to n whatever dimension arrays. How does that all work?
So, a 2-dimensional array, you would look at like a chessboard, where you say, I'm going to move my chess piece A4 to A6.
Or up 1 over 2.
Right,
like
whatever.
That. Yeah.
So a 3-dimensional array is kind of more like a Rubik's Cube. But imagine that the Rubik's Cube is filled with all of the subcubes. And you can refer to any one of those individual cubes that make up the Rubik's Cube. That would be more like a 3-dimensional array. 4-dimensional arrays become very difficult to represent physically. So they're often represented by using another constraint of time. So imagine a Rubik's Cube that the values change over a course of time. That's a 4th-dimensional array. 5th-dimensional array, we'll need to smoke a bunch of weed and sit down for a while. That's the only way I could.
That's the only way we could get that out of you.
6th dimension, peyote. 7th dimension is acid.
Well, just I mean, those are all great examples, but there are technically no limits to the dimensions of arrays. As long as you have memory to store it,
absolutely,
you can use it. I find a practical reason for a 7-dimensional array, and we'll sit down and I would love to pick your brain because you are a very smart person. So as Brian said, and this may be overkill at this point, but this is just kind of a basic representation of a 2-dimensional array. This is an addition table, or is it it's multiplication table, where the top line is index 0 through 3, and then the left side is the sub-index 0 through 4. So if you wanted to kind of use this practically and just kind of see how it works, 3 on the upper right-hand corner times 4 on the bottom left-hand corner will equal 12. And that's how this basically...
So if you were to store these values in this table, you could use that 2-dimensional array as an addition table. Or as a multiplication table. Instead of using multiplication in your program, you could actually look up a value in this table to get your multiplication. It's probably easier to multiply, but that's the concept.